Hey, Calc students, this is Mr. Beck. Today we're going to be talking about a couple different sections, and both involve trigonometry, which is one of my favorite topics. Calculus is my favorite topic, but then you combine it with trigonometry, and then you have something absolutely beautiful. So before we begin, what I'd like to do is talk about some of the double angle formulas. I don't know if you guys remember double angle formulas from trigonometry. Sine of 2x equals 2 sine x cosine of x. That's going to be one of the ones that I do expect you to know really, really well. The other big one that I expect you to know really, really well is cosine of 2x is cosine squared minus sine squared. Now, that's the one that I'm hoping you remember, but remember we have two other forms of the double angle formula for cosine. 1 minus 2 sine squared, which if we use the Pythagorean identity, sine squared plus cosine squared equals 1. That's how we get that one. And it's also how we get that one down here, 2 cosine squared minus 1. Now for today, we're going to be doing some work with these double angle formulas, but we are going to do what we call the power reducing formulas. So it's just a quick manipulation of those equations to get sine squared equals 1 minus cosine 2x over 2. So if we subtract cosine, add sine squared, add the 2 sine squared, and then divide by 2. Same thing with the second equation down here. It is a double angle formula, but we can manipulate it to what we call the power reducing formula to turn the cosine squared into 1 plus cosine 2x over 2. I mentioned the Pythagorean identity, sine squared plus cosine squared equals 1. Remember, if we divide everything by cosine squared, we will get the second of the Pythagorean identities. Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared. And then if we take the original Pythagorean identity and divide by sine squared, we get 1, cotangent squared, and cosecant squared. So these are a bunch of big Pythagorean identities that we are going to be working with today, Pythagorean and the double angles. So our first primary question is, how do we integrate this cosine cubed sine to the fourth power? The cosine cubed sine to the fourth. Let's take a quick walk to see where we've been in terms of graphing or finding the integrals. So the integrals that we've taken are what happens if we have sine of x, cosine of x, dx. If you remember, we could do u equals sine of x, and then cosine of x dx is going to be your chain. What happens if we take u equals sine of x, then du is, oh, sorry, that's the one I just did. How about u is cosine of x? My apologies. Then du is negative sine x dx. So we could work with that one. We also did some integrals where we said what happens if we are finding the integral of sine cubed x cosine x dx. We said, okay, let's let u equal sine of x, and that's because this is going to be du. So really, we did integrals where we just had like one trig to a higher power, and then the other trig is just the first power. So our question now is, what happens if we have the integral of cosine cubed sine to the fourth? What we're going to do is we're going to use this as a guideline for us. What we want is we want to have a cosine x dx or a sine of x dx. We want to have that as our overall chain. So when we have this as our overall chain, what we're going to do is we are going to break up the cosine cubed into cosine squared times cosine. Now, I said this is what we're doing, but really, what's the purpose of me doing this? The purpose of me doing this is I am looking for one of the cosines to be taken out so that I'm left with even powers. The reason why I care about even powers is because we can turn sine squareds into cosine squareds and cosine squareds into sine squareds using this overall almighty Pythagorean triple or Pythagorean identity, the sine squared plus cosine squared equals 1. So our hope is one of these is odd, one of these is even, and when we go to do our u substitution, u is going to end up being the even exponent, because the odd exponent then it becomes a chain, making that even, so we could turn it into 1 plus sine squared. So that's exactly what I did. And then here I distributed the sine to the fourth power to both terms on the inside. I did leave the cosine x dx because really that's modeling u to the fourth minus u6 du. Then we do our integration, and we're back to integration, so don't forget your plus c. Now what I did, by the way, this is a very valid and very happy answer. What I did was I decided to play with it a little bit more because sometimes you might see your answer in a slightly different form. You might say, why is it that way? Or is my answer the same thing as what the back of the book has or somebody else has? So what I did was I first combined into one fraction, and then the reason why I did that was because then I broke the 7 sine to the 5th into 2 sine squared plus 5, sorry, 5 sine squared plus, that is supposed to be 2 sine to the 5th power. Typo. Hate it when I find typos on the video notes, but hey, we're all human. So 2 sine to the 5th plus 5 sine to the 5th. And when we do that, yeah, that's supposed to be sine to the 5th all the way down. So when we do that, what it allows us to do is break it apart into sine to the 5th plus, or we factor out the sine to the 5th from the second equation. And what ends up happening is we have a 1 minus sine squared, which we could turn into cosine squared. Then the question becomes, why would we want to do that? Well, we continue doing some factoring. We could factor out the sine to the 5th, and then we're going to have a 1 plus cosine squared. We could do something with that, hopefully, maybe, we don't know. Remember, sine squared plus cosine squared equals 1. So there are a lot of different things that we could do that could possibly be fun. Now, as I said, this is a very happy answer, and I'm going to leave the answer that way. But there are going to be some occasions where we might want to do this to come up with a different answer or really apply it in a different context. For my second problem, excuse me, this should be fairly natural to you. U should be cosine of t because it is inside the composition of functions there. So if u is cosine of t, du is negative sine t. So this is just a quick rewriting. Negative, notice how sine to the 5th, what I did, and I didn't show it, but I broke that up into negative sine to the 4th t times negative sine t dt, because that is my du that I have here. Then I turn my sine to the 4th into sine squared times sine squared. Now this is a great situation where we turn the sine squared into 1 minus cosine squared. So don't forget that sine squared t is 1 minus cosine squared t. And from that, then I, since cosine squared is cosine is my u, 1 minus u squared times 1 minus u squared, multiply it through, and then I turn that denominator into u to the negative 1/2. Distributed, and now I do everything by power rules, which is pretty easy. And then that would be our cosines when we resubstitute. So kind of a fun problem to do on one level. On another level, it's kind of similar to what we've done in the past, but we're about to get very, very different. So what do I mean by that? Well, let's look at example 3. Now, I don't know if you remember when we talked about 7.2, one of the big topics that we talked about in 7.2 is what happens if we, which is integration by parts. What happens if we do integral sine of x times sine of x? We can integrate by parts and say this is u, this is dv, and then we could play around. And one of the ideas behind this was I equaled the integral of sine squared x dx. And as we do our integration by parts, we're going to have some stuff plus the integral of sine squared x dx, which we can then call I, and then bring that over. Usually it's like some fraction of I, let's say 1/2 or 1/3. I don't remember exactly what it was. But then we can combine our i's together. So this is a creative version of solving the integrals. Now what we're going to do instead is we are going to turn the sine squared and use the power reducing formulas, 1 minus cosine 2x over 2, which I do like to bring that factor on the outside as much as possible. Once I bring the factor on the outside, then I have 1 minus cosine 2x, which is nice and integrable. So then distribute it to 1/2 to get my final answer. Much easier than doing the integration by parts. Just requires us to remember using that power reducing formula. Example 4, we have cosine to the 4th power. So what I did was I turned that into cosine squared, which then power reducing, yay, I love the power reducing formula. Really, I just love trigonometry. So once I have that, I did bring out the 1/4 just so that I could focus on that 1 plus cosine 2x squared. Once I multiplied all of that out, then I realized, hey, I have another cosine squared that I need to use the power reducing formula one more time. So that's what I did. And then let's clean it up. 1/4 times 1 times or plus 1/2 times 1/4 gives me my 3/8. That ends up being 1/2 cosine 2x and 1/8 cosine 4x, which then I directly integrate into 3/8 x plus 1/4 sine 2x plus 1/32 sine 4x plus c. So far, so good. I'm really hoping so. Now, because we did a lot of work with the integral of sine squared, the integral of cosine to the fourth, because if you notice the difference here is we have a mixture of sines and cosines, and our differential is how we really approach it. We said we took a look and said sine and excuse me, sine x dx or sine t dt is our differential for our chain. Here, we didn't have both the differential or the chain. We basically just had one of the trig functions to a power. And since we had a trig function to a power, then we were able to solve it as an indefinite integral. Now, Wallace's formula, Wallace is a famous mathematician. Wallace's formula, what he did was he proved that if we take the integral from 0 to pi over 2 of cosine to any power, it's going to equal this fractional relationship. 2/3 times 4/5 times 6/7, really times n minus 1 over n. For those, let me just leave it at that. So that is if that exponent is odd. So what we're doing is if that exponent is odd, then we get those odd denominators. Now that comes from, we can see a little bit in that work from the problems that we did up here. We had 1/5 plus 1, or we had 1/5, 1/7. So that's where it comes from. Notice how that was an odd power of cosine that we ended up working with. But anyway, we had 2/3, 4/5, 6/7. Now this could be true for sine as well. If this is the integral of sine to a power, it ends up being the exact same thing. Oddly enough, not really oddly enough when you think about the Pythagorean triple, but anyway. If we have an even exponent, then we have the even exponents on the denominator. Same kind of idea, but slight difference is we are multiplying by pi. So where we would use that as a situation is what happens if we are revolving y equals, let's just say sine of x. That sine of x, if we're going from 0 to pi over 2, if we're revolving that and finding the volume of the shape that we're revolving, that would be the integral from 0 to pi over 2 pi sine squared x dx, because it's pi r squared. We could use Wallace's to show that this is going to be equal to 1/2, because n is 2, and then times pi over 2, which gives us pi over 4. So that's an application of Wallace's formula. I mean, that one is important that we know how to do that. We could really do that with the power reducing formula if we wanted to. That is great. I have no problem with that. But this gives us a lot of flexibility to figure out how to do some of the problems. Anyway, this integral, problem number 5, and I have a problem number 6, integral of sine in the ninth. The reason why I need that 9 is because that's where I end up, n minus 1, and just work our way backwards. And this one simplifies to 128 over 315. On example number 6. Example number 6, if I'm going to integrate cosine to the 10th power, then n minus 1, work our way backwards, get 63 pi over 512. What I did in class was I had students use the graphing calculator just to verify these results are accurate, and they were, ironically. So, moving right along. What happens if we have problems that involve secant and tangent? If we have secant and tangent, then we're going to do something very similar to what we just did up above. That similarity is going back to, we know that tangent squared plus 1, if I can zoom in, we know that tangent squared plus 1 does equal secant squared, and so we're going to be using that bit of information. The other bit of information that we're going to work with, obviously I have it on side here, is if we remember the derivative of tangent is secant squared, and the derivative of secant is secant tangent. Now, the reason why we need to know all of that information has to do with the fact that when we take a problem such as, I'm going to look at this secant to the 6th power, if I just have secants, what I need to think through is, okay, I know that secant squared, in this case it's going to be 3x, but I know that secant squared is the derivative of tangent. So if secant squared is the derivative of tangent, I could break this into secant to the 4th of 3x times secant squared of 3x, because this is my derivative that's going to be part of my chain. So that's our goal, which means we need everything else in terms of tangent. Well, is there a way of taking secant to the fourth into tangents? Why, yes, there is. What we could do is we could say that's tangent of 3x plus 1 squared. And then I went ahead and FOILed it out. And I also brought out the chain. So if I have secant squared of 3x dx, that derivative is really 3 dx. So I wrote out the 1/3 as well. And then if I say u equal to tangent of 3x, then I have u to the fourth, 2u squared plus 1. I went ahead and took the antiderivative and then distributed through. So far, so good. I really, really hope so. So when it comes to this problem, this is going to be a mixture of secants and tangents, and that's a little bit of an indication that, okay, we're going to have one of two things happening. We are going to have either secant squared, and as my derivative, just kind of like what we had before. So the secant squared is going to be great if we have, if we set u equal to tangent. Now, in this case, what is going on is because both of these are odd exponents, by factoring out both the secant and the tangent, it turns these into even exponents. And remember, we want those to be even exponents, so we could use the trig identity up here. So our goal is to turn everything into even exponents as much as possible and work with the derivative. So that derivative tells me u is going to be secant, because otherwise I could have the choice of either one, but the derivative tells me u is the secant. So we're using that as our kind of guiding force. So since u is secant, I turned my tangent into secant squared minus 1. I went ahead and distributed and put it in terms of u. And this is my du. Notice how I didn't forget my chain there. It's important not to forget that chain. And then took the integral and distributed it through. Yay. All right, then, so we're done with a lot of the overall like trig integrals. This will work for cosecant and cotangent as well. What I have here, if you want to pause and take a look at that and really study this, the only difference is what happens if both of them are even exponents. This is true for sine and cosine as well. Integration by parts tends to be the approach that we take for that reason. But you can look at these overall guidelines. What I don't like about written guidelines is that students tend to be like, oh, I must follow these exact guidelines. What I would prefer you to do is look at the equation and say, how can we play with this? How can we work with this? How can we manipulate this? Manipulation should give you that approach. And it's more of the, what am I looking for that will tell me how to do the problem. And my hope is that you guys have this. If you are still not sure, you have any questions, we can follow the guidelines. But the guidelines should be more intuitive as you get through and work through the problems to say, why doesn't this work? And please don't be afraid of failure or trying something and you realize, hey, that doesn't work. That's actually the process of learning. That learning of, okay, this doesn't work, so we're going to try something new and see what happens. That is how you get better and to figure out how to approach the problems. But anyway, on to our next topic. Our next topic, my question is, and I'm trying to just zoom in. So what is the integral of, from -4 to 4 of 16 minus x squared dx? That answer is 8 pi because we can think through this geometrically. We think that this is a semicircle with a radius of 4. Semicircle with a radius of 4 then says, okay, 1/2 pi r squared, aka 8 pi. That is great. That is awesome. That's amazing. But is there an algebraic way we can do this? So that's our driving question for this kind of problem. How do we approach this algebraically? So I think since this involves a circle, trigonometry is most likely involved with this, and it turns out it really is. So I said, okay, let's let x equal 4 sine theta. So if x equals 4 sine theta, what ends up happening if I do that substitution, I get 16 minus 16 sine squared. Why we care about that is we could write that as 4 times the square root of 1 minus sine squared. Ignore everything else temporarily. And the square root of 1 minus sine squared is the square root of cosine squared, which is just cosine. So the driving force for why would I think about doing that kind of substitution is because when I do the substitution, I end up with something really, really nice. That is cosine of theta. But then we have to clean everything up because cleaning everything up is really, really important. What we had was this is dx in terms of x. So we have to find dx from x equals 4 sine theta. We have to find our dx, which is 4 cosine theta d theta. And that's what I have here. And of course, if I change from x to theta, I also have to change my limits, -4 and 4. So I solve for sine, and we get what is the inverse sine of -4 over 4? That would be -5/2. What's the inverse sine of 4 over 4? That would be pi/2. And then now we have our overall integral. And let's multiply everything out. This would be cosine times cosine, which is cosine squared. Notice how I went from -pi/2 to pi/2 of an even function. So that's the same thing as saying 32 times the integral from 0 to pi/2 of cosine of theta d theta. Wait a second, didn't we just talk about the integral from pi/2, or from 0 to pi/2? That would be Wallace. We could use Wallace's formula to show why that answer was actually 8 pi. By the way, what I have over here is what I mentally did up there. Or we can go ahead and work it out using the power reducing formulas and we'll get the 8 pi as well. So what I did, if you remember, I said, okay, x equals 4 sine of theta. And the reason why I chose 4 sine of theta because I knew that this would work out to something nice, which is x sine of theta. So how did I know this? Well, if you look at our triangle, if we could build the triangle that creates that radical, that's why we're allowed to use trigonometry. So the question now becomes, okay, how do we build the proper triangle? And so to build the proper triangle, what I'm going to encourage you to do is look at your inverse trig. So on your inverse trig, if you remember, the derivative of arcsine was dx over the square root of 1 minus x squared. Derivative of arcsecant, that was going to be important, and the derivative of arctangent, dx over x squared plus 1. All right, we could use this as a guiding force. If we have the square root of a squared minus x squared, so if we have the square root of a squared minus x squared, that tells me we should be using arcsine, and we can build the proper triangle. If I have the derivative of x squared, or if I have x squared minus 1 as my derivative, that is my indication that I should probably be using secant in order to create my triangle. And if I have x squared plus 1 underneath the square root, then that tells me that tangent is going to be used to draw my triangle. And those triangles we can see right here at the top of our next page notes, that if we set u equal to a sine theta, we could really look at this as sine of theta is u over a, and we could use that to build the triangle. Now, I do like to emphasize u equals a sine of theta, u equals a tangent theta, u equals a secant of theta, because that kind of substitution is what we tend to go for. So for instance, if you notice on problem number 1, trying not to show too much here, if you look at problem number 1, I see a squared minus x squared. That's my prompt that x equals 3 sine theta. Because it's a squared minus x squared at sine, my a value is 3. So my u, if you remember, this is u squared, this is a squared. So that's why it's u equals 3 sine theta. On problem number 2, we could look at this also and say, this is my u. So that's u squared, excuse me. This is u squared. So u is 2x. And because it's u squared plus a squared, this is 1 tangent of theta. So 2x equals tangent of theta. On this problem, what we have is x squared plus 1. Because it's x squared plus 1, that's tangent. And this is u squared. So that's u is just x. This is a squared, so a is 1. So x equals 1 tangent of theta. So knowing what the substitution is going to be very, very important as you go to do the problem. Again, which trig function should we use is based off of the triangle that creates that form of the radical. So then we get into the problems. How do we do each one of these problems? We purely just do the substitution. So by doing the substitution, x equals 3 sine theta, it turns this radical into 9 minus 9 sine squared theta, which when we factor out the 3, square root of 1 minus sine squared, which turns into 3 cosine. Now, if you notice, I canceled it out because when we do our cleanup work, which I'm not sure if I showed that derivative here, dx is 3 cosine theta d theta. And so we did our substitution, 3 cosine of theta d theta right there. And those cosines ended up canceling each other out. So simplified turns into d theta over 9 sine squared, which, if you remember, 1 over sine squared is cosine squared. And this is kind of the cleaned up version of that result, which gives me negative 1/9 cotangent theta plus c. Now, here's the question. What is the cotangent of theta? Well, the cotangent of theta really is based off of the triangle that formed this relationship that we did the substitution. That's probably a good indication that we should draw out our triangle right from the beginning, unless you're good enough to know what it is. We should draw out our triangle to figure out that relationship. Remember, the substitution we did was x equals 3 sine of theta. Then we know that sine of theta is x over 3. So we have our theta, we have our x over 3, and to form the radical 9 minus x squared underneath the square root. So now that we've drawn our triangle, let's go back and say, what is cotangent? If you remember, cotangent is x over y. So we did our substitution, our x over our y. So negative 1/9 times that plus c, and that's just written all together. On the second equation, if you remember, we did the 2x equals tangent of theta. And I'm trying to hide the work right now just to show you maybe it's a really good idea right from the beginning to draw out our triangle. If 2x equals tangent of theta, we could draw our triangle so that theta, our tangent of theta is 2x over 1. And we could draw that square root of 4x squared plus 1. Now, if this is our substitution, then dx will be 1/2 secant squared theta d theta. Let's go ahead and show you all the work behind this one. So remember, our initial problem was dx over the square root of 4x squared plus 1. So we did our substitution for dx, right so. And then we said 2x was tangent of theta, so we substituted tangent of theta for 2x, so that's really 2x the quantity squared, or tangent squared, plus 1. Tangent squared plus 1 is secant squared, and the square root is secant. It actually is the absolute value of secant, so there are going to be some things that we are going to have to watch out for. We're not going to really face a whole lot of them today, but in the future, we'll talk about them when we get into a lot more of the applications of the trig substitution. But anyway, the square root of tangent squared plus 1, let's go ahead and just say it's secant for now. So this ends up being the integral of just secant. And if you remember, the integral of secant is the natural log of the absolute value, secant plus tangent. Well, what is secant of theta? We go back to our triangle and say secant is radius over x. So that would be the square root of 4x squared plus 1. Tangent of theta, that was our substitution right from the beginning. So plus 2x and then plus c because this is an indefinite integral. Problem number 3, if you remember, we did that substitution, x equals tangent of theta. So dx is secant squared theta d theta. We did our substitution. This ends up being, if we draw our triangle out, x equals tangent of theta. So tangent of theta is opposite, or y over x. So x is tangent of theta. That leaves my hypotenuse. Now, that x square root of x squared plus 1 ends up being our x ends up being secant. And the way I did this problem was I looked at these 3 parts. I looked at the radius over our x is the secant of theta. So I immediately turned that square root into secant of theta, but then it ended up being cubed. So I have a lot of students who do like to immediately go and use the geometry, use the triangle to create that relationship. And I'm showing that with this problem. Now, algebraically, could we do the same substitution that we did in example 2? Absolutely. Anyway, long story short, secant squared over secant is, secant squared over secant cubed is 1 over secant, which is cosine of theta, which integrates into the sine, which then we go back to our triangle and figure out what is the sine of theta, and then we come back and say it is that x over the square root of x squared plus c. All right, so let's lead you through some problems. What do I see on this problem? I see a squared minus u squared. That tells me it's sine. That does say sine, believe it or not. Okay, so that tells me it's sine. And if a squared is 25, a is 5. And if u squared is x squared, u is x. So x equals 5 sine theta. Draw the triangle. That triangle of x equals 5 sine theta or sine of theta equals x over 5, whichever way you need to look at it to draw the triangle. Now I can find my differential. Dx is 5 cosine theta d theta, which I do my substitution, and I do the other substitution as well. And this turns into 5 cosine theta over 5 cosine theta d theta, which is just the integral of d theta. Amazing. So theta plus c, and theta is the arc sine of x over 5. And this is where I usually go, wait a minute, to have such a nice, clean answer like that. Oh yeah, this problem really was an arc sine problem right from the beginning, so we could have gone to the answer. But this is actually the trig substitution shows why it works, which is really, really cool, and I like it a lot. All right, example number 5. Example number 5 is probably my most favorite problem on this, just because there's a lot of random math comes into play. So break out your math toolbox, and what skills do you have that we're going to need to use? So the first thing we did was, this is a completed square, and that completed square is 2 plus x, the quantity squared. That's really 2 plus x squared, the quantity squared. And then because I have 2 plus x squared, that's which of the 3 trig functions? That would be the u squared plus a squared. So u is just x, a is the square root of 2, and it's tangent because it's the a squared plus u squared. So dx is the square root of 2 secant squared d theta. Now let's go into our substitutions. So this is the square root of 2 secant squared. Actually, I take that back. This would be the square. It is, okay, so it's the 2 plus x squared, which I replaced that with tangent squared. What I did on this problem, sorry for the pause on that one, dramatic pause. What I did is I did it more by the geometric way. Let me show the algebraic way on that one. So if x is the square root of 2 tangent theta, that turns this into 2 plus 2 tangent squared theta, and that whole quantity squared. If we factor out the 2, that's what gives us the 4. That 4 is where this comes from. And so this is now 1 plus tangent squared theta squared. And that 1 plus tangent squared theta is secant squared theta. And that secant squared is where we get the secant to the 4th. So when I initially did this, I did it straight from the geometry. I am honestly not quite as straight, or I'm not as good looking at the geometry, which is why I tend to prefer the algebra. But we could do this geometrically as well, just like I did in example number 3. But anyway, so we have secant squared over secant to the 4th, which we could reduce to cosine squared. Unfortunately, this one is not a 0 to pi over 2, so Wallace's formula is not going to apply there. So we have to use our power reducing formula, 1/2 of that coefficient, and then 1 plus cosine 2 theta. So that turns into square root of 2 over 8 times theta plus 1/2 sine 2 theta plus c. But this is where we say, ooh, once again, I really don't want theta. I want this in terms of x, so we're going to use the double angle formula for sine, which is 2 sine theta cosine theta. And I needed my triangles so I could figure out what my sine of theta is and what my cosine of theta is. And I get this beautiful expression right here, which all I did was multiply it out to get my final answer. Absolutely beautiful problem. Lots and lots of fun. Lots, as I said, random skills. We use some double angle formulas in there. We use some power reducing formulas in there. We did our trig substitution in there. Absolutely beautiful. And then last but not least, we have this problem, which is a definite integral. The fact that I'm seeing a 1 minus t squared prompts me that we have sine, because it's a squared minus u squared. So u is just t, a is 1, and we have that expression. So dt is cosine theta d theta, which is what I have here. And working that all out, we have cosine over cosine squared to the 5/2, which is cosine to the 5th, or that overall is 1 over cosine to the 4th, which turns into secant to the 4th. And this is where we just did some problems like this on the previous page. If I have secant to the 4th, I need to factor that out. So I have a secant squared times secant squared. But one of those secant squareds I'm going to turn into tangent squared plus 1, or u squared plus 1, according to the problem that we're doing. So u is tangent squared, du is secant squared theta d theta. So what's beautiful about this problem is it started with t, we took it with a trig substitution, And now with that trig substitution, we're working with a new substitution. That new substitution allows us to see things a lot more clearly. Now keep in mind, as you're working through the problem, I said, what is the inverse sign of the square root of 3 over 2? That gave me pi over 3. The inverse sign of 0 is 0. So we changed our limits for that problem. And then once we changed our limits by going to the new variable u, then we said, okay, u, I'm not sure if I actually have that written anywhere specifically here. So u is the tangent of theta. Since u is the tangent of theta on this one, then tangent of pi over 3 is the square root of 3, so we had to change our limits one more time. And then we integrate and we get 2 square root of 3. Another beautiful problem, a little bit creative, a little bit of fun. I hope you guys enjoyed it just as much as I did, and I will see you next time.